Okay. Good afternoon, everyone. I'm going to talk about 3 ways to measure and communicate the cost of underfunding maintenance. The first one is the maintenance backlog in forecast annual spending needs. We can get that for the first year, or we can average it over a period of years, and you can compare that with actual or budgeted spending. The second one involves benefit cost ratios or marginal benefit cost ratios, and they're useful because we can compare them with benefit cost ratios for capital projects or the cut-off benefit cost ratio for capital spending. The third concept, equivalent interest rate for deferred maintenance, looks at maintenance deferral as a form of borrowing. You save money in the short term, but you have to pay more later on. And you can compare that with the interest rate for government borrowing. So I'm going to refer to a case study and model. My case study concerns the non-urban parts of the national network in the Australian state of Victoria. That's in the southeast corner, in case you don't know. Nearly 2,000 kilometres, it's mostly sprayed seal pavement, and for analysis purposes, we divided it into 573 strategic segments. We engaged ARB Group to calibrate HDM4 for us, and they put together the data too, using monitored test sites. With the data and calibration coefficients, there were 2 modelling exercises. ARB did it for us using HDM4, working with Vic Roads, and then I've developed a spreadsheet model using simplified HDM4 algorithms, and gives me a lot more flexibility having a spreadsheet model. Most of the results here will be from my model. These models exclude routine maintenance except for patching potholes. It's only periodic maintenance. I've listed there the main elements that go into the model: a deterioration algorithm, some alternative treatments, a road user cost relationship, technical constraints, budget constraints, and optimisation. This shows the main processes and drivers within the model. Cracking, pavement strength, rutting and potholing, they all feed into determining roughness progression. Cracking feeds into everything. Then some of the main drivers are the initial pavement strength, pavement age, surface age, axle loadings, climate and environment. I might add that potholing is not very important here because I've assumed that they're patched fairly quickly, being on the national network, the highest level of roads. These charts show what model output for a brand new pavement. It's a sprayed seal pavement with weighted average characteristics with and without resurfacing. So the red line shows, if we look at the cracking one, nothing happens till after about 10, 11 years after the bitumen oxidises, and then it follows an S-curve. The blue curve shows what happens when we do a resurface every 11 years, so we prevent cracking from taking off. As you can see, when there's cracking, it affects the pavement strength. It doesn't have much effect on rutting, but the reason for that is because this is a very strong pavement, a structural number of about 7, and a relatively low traffic level. That gap for rutting will be much higher if we had a weaker pavement and more traffic. But even so, it makes quite a difference to roughness progression in the long term. In fact, taking roughness up there to 10, that's simply extrapolation. The pavement is wrecked, basically. We have 4 treatment type options. A resurface, which is an overlay of 10 millimetres for sprayed seal pavements and 20 millimetres for asphaltic concrete pavements. Resurface with shape correction, which is an overlay twice as thick, and then partial and full rehabilitation. The partial one restores pavement strength to 90% of Australia's design standards, and the full rehabilitation to 100%. The model never, under any circumstances, chose full rehabilitation, which makes me wonder if perhaps Australia's design standards are on the high side, at least from an economic point of view. Each treatment has a cost per square metre, and those costs go up with the condition of the pavement. So if you let it get more cracked, there's higher cost. And if the structural number is allowed to fall too far, that also adds to rehabilitation costs because you have to replace more layers of the pavement. The treatments have reset impacts. All of them reset surface age and cracking age to 0. The resurface has very little effect on roughness and pavement strength. Resurface with shape correction knocks about 1 IRI unit off the roughness, has some effect on pavement strength. Rehabilitation, in effect, creates a new pavement with a roughness we've assumed of 1.2. Other key model features are, I've done it over a 40-year analysis period, a 4% discount rate. Now, we can set it up either to minimise the present value of total transport costs or road agency costs. Total transport cost is the sum of road agency and road user costs. There's a road agency cost includes the residual value. The purpose of that is to stop the model from pushing the last treatment out just beyond the analysis period. The model tests all feasible combinations and timings of treatment. That means it does 18.5 million trials to get through the database, runs overnight, and optimisation subject to annual budget constraints is performed in separate spreadsheets. These are the user cost relationships. They look different from the ones you saw in the previous presentation because I've set them all at 0. I've assumed that for roughnesses below 3, there's no effect on user costs, and then I've made it quadratic so as to rise gradually. At first up to 4.5 and then it becomes linear. So looking at the optimisation, this is what minimising total transport costs mean. I've got the present value of agency costs on the horizontal axis and also dollars on the vertical axis. So present value of road agency costs is a 45-degree line. As we spend more on the road and improve the condition, user costs go down, and once we get to keeping roughness below 3, they go to 0. You add those two curves together, you get a U-shaped curve, and you can see where the optimum is. This is the forecast expenditure needs for the first 20 years, comparing HDM4 as modelled by ARB and my model. The individual years can vary considerably. In ARB's HDM4 model, first year spending is 123 million, for mine it's 117. Averaging it over the 10 years, 63 million for ARB's model, 74 million for mine. So they're roughly in the same ballpark. However, actual spending on this part of the network in Victoria, at the time the data was put together, was round about $15 to $20 million a year, about 25% of the optimum requirement. Just a few sensitivity tests, as I've already noted. Annual spending needs can be very variable from year to year. I've found, trying out different assumptions, the first year value can vary greatly. It's more stable to average the expenditure needs over the first 10 years, and it's probably a better measure. Just a few sensitivity tests. If I increase the discount rate from 4 to 7%, it reduces first year spending by 38%, but there's only a 4% reduction in the 10-year spending. ARB and I had a bit of a problem with pavement strength. We didn't have any data on that, so we've assumed that the roads have been designed according to Australia's design standards. If we plus or minus 20% change in the initial pavement strength changes the 10-year average by minus to plus 18, 20%. but it makes a very big difference for the first year. If we reduce pavement strength by 20%, then because many of these pavements were built a long time ago, our estimate of pavement strength right now is much lower, so it has a huge increase in first year costs. If we want to calculate a benefit cost ratio for an individual maintenance treatment, there are a number of conceptual difficulties. There's numerous options for different treatment types and timings, and the base case is arbitrary, because you can't just do nothing. Benefit cost ratios make a lot more sense when we do it for a whole network. So if we were going to increase the present value of road agency costs by a large amount, we could define the benefit cost ratio as the ratio of the saving in user costs to the additional agency costs. And we have to put a minus sign there because it's a saving in user costs, they go down. For a small increase in spending, we can talk about a marginal benefit cost ratio. It's 1 minus the slope of the present value of total transport cost curve that I showed you before. Just to give you an example, if we set the marginal benefit cost ratio of 3, so we've moved somewhat up to the left of that U-shaped curve, first year spending isn't affected by much, but 10-year spending goes down by 41%. But the present value of total transport cost is $114 million more. It's very easy to do that in one of these models. You just apply a weighting of 1/3 to user costs and let it run. Marginal benefit cost ratios for a whole network can be useful because they can give us information on the value of shifting funds between maintenance and capital spending. If your relative sizes of your maintenance and capital budgets are optimal, you would have similar marginal benefit cost ratios. In the case of capital budgeting, you would rank projects by benefit cost ratio, as you can see on that diagram there. You would do the projects in descending order until you run out of funds, and your cut-off benefit cost ratio is the benefit cost ratio for the last dollar invested. So let's say your marginal benefit cost ratio for maintenance was 4 and your cut-off benefit cost ratio for capital was 2. If you shifted $1 from capital to maintenance, you'd lose $2 on capital, but you'd gain $4 for maintenance. So it can be quite useful to know the marginal benefit cost ratio for maintenance. However, this marginal benefit cost ratio, as I defined it previously, assumes that the budget constraint is a present value, and that would only be realistic if the road agency could shift funds through time by borrowing and lending at the discount rate, which is not realistic. So for short-term budget constraints, I've suggested an alternative definition for the marginal benefit cost ratio. PVB is the present value of annual budget increases. Let's say you're looking at a period of time, 3 years, 5 years ahead, whatever your budget is. You look at an increase in spending just for those few years. So on the numerator, you've got the saving in user costs as before, but you also have to add in the saving in agency costs. After you've increased your short-term funds, there's savings in road agency costs. Now, because the present value of road agency costs includes costs in the first few years, it's already got the present value of the budget in it, multiplied by -1. So I have to add back in PVB to cancel them out. And if the present value of your budget increase was the same as the present value of your total change in agency costs, the formula would reduce to what I showed you before. So here's an example of using that formula to calculate a marginal benefit cost ratio with short-term budget constraints. So in my case study, I said before that we believed that actual spending was about 25% of requirements, so that's about $18.5 million. If I relax that constraint to $28.5 million, you can see I've shown you the numbers there. Saving in user costs $14 million. Agency costs end up being $4 million less, even though you're spending more in the short term. And the present value of the budget cost is $44 million. So applying my formula, it comes up with a benefit cost ratio of 1.4. And I was quite surprised when I did this. Why is it so small? I thought it'd be much larger than that. Well, the trouble is that I'd only set the spending constraint for the first 5 years, and the backlog was very quickly eliminated. What's happened is it's just pushed maintenance all into year 6, which is spiked up to over $500 million, which is quite unrealistic that you could spend that much money in 1 year. So in order to operationalise this formula, you need to carry on your spending constraints further. So I've got 3 scenarios in this slide here. These blue ones show what happens when I've just capped it at the 10-year average of $74 million. And there's a fair bit of constraints in the latter years which are not met. So we've got a bit of slack there to fill up. When we press down on spending in the first 5 years, it pushes it up in the latter years. It can't go up above as in the previous slide, so it's got to be pushed into the future. And you can see that the orange and green lines are much higher there. So working out the benefit cost ratios using my formula, if I relax the constraint from 18.5 to 28.5 million for the first 5 years, I end up with a marginal benefit cost ratio of 4.2. And I can call it marginal because it's not a very large increase. If I had a very big change in the constraint from 18.5 to 74.5, then I end up with, first of all, I call it a benefit cost ratio. It's not marginal anymore. And I end up with a benefit cost ratio of 2.3. What's happening there is as you put more money into the maintenance budget, there's diminishing returns. The first few dollars give you the biggest return, and then it gradually falls off. So the bigger your assumed change in spending, the lower will be your marginal benefit cost ratio. Right up at the constraint, where it's $18.5 million, the marginal benefit cost ratio is around 11. Now I want to look at another approach, which is a more realistic approach for a cash-strapped road agency, where you minimise the present value of agency costs subject to minimum standard constraints. And this is a financial analysis really from the point of view of the road agency, you would discount at the government's borrowing rate. I've chosen some minimum acceptable standards. These are based on Australian government standards for the national network, and it's the boundary between mediocre and poor ride quality standards. The standards are higher where traffic is higher. So when I run this scenario through my model, the average annual spending needs for the first 10 years is $65 million per year. It's a bit lower than the $74 million that I came up with before, minimising the present value of total transport costs. So I tried to get it down to that $18.5 million for the first few years, and I found that with these minimum standard constraints, I could only hold it for 3 years. It had to rise after that, otherwise you'd fall below the minimum standards. And then I've used constraints in later years to smooth the expenditure profile. Short-term budget constraints save money in the short term, but they can cost you more in the long term. The long-term costs can outweigh the short-term gains, even with discounting. Introducing these very tight short-term constraints increases the present value of agency costs by $96 million. So that's one way to measure the costs of maintenance deferral to the government. But the one I was most interested in is what I call the equivalent interest rate from deferred maintenance. This is the internal rate of return for the difference between the cash flows for the cost minimising and budget constrained spending profiles. So here's my two spending profiles that I'm comparing. The green one, I've just set an upper limit of $65 million for all years. And then in my constrained one, $18.5 million for the first 3 years. But then in order to keep those minimum standards, I have to increase it quite considerably in later years. I just have no choice. So what I've done next, is to take the difference between those two scenarios. So you can see in the first 4 years, the short-term tight budget constraints have saved us money and we're effectively getting a positive cash flow. But then once we get beyond year 5, where we've got to catch up on the backlog to keep within the minimum standards, we're having negative cash flows. So if I work out the internal rate of return of that series of cash flows, it ends up being 12%. That's a very expensive rate to borrow money. It would be better for the road agency if it could borrow to fund the extra maintenance in years 1 to 4 and then pay back the loan later. The cash outflows when it's repaying the loan between years 5 to 12 would be lower than spending it on maintenance. So just to sum up with the lessons learned, I've covered 3 ways to measure and communicate the cost of deferring maintenance. And by focusing on marginal benefit cost ratios and looking at it as borrowing, it's language which government finance ministries should be able to understand. I've also found in the course of the modelling that model results can be very sensitive to assumptions. So it's very important to have good data and model calibration. There's been a whole lot of other lessons which I haven't covered today on modelling and optimisation techniques, which will be presented in the forthcoming report, which I have to get back and write very soon. I just want to add that all the figures I presented today are preliminary and they will be different in the report because I'm going to review all the modelling and rerun it all. Thank you.